In the last video, we looked at a bunch of vocabulary words concerning functions, and in this video we're going to look at some theorems about functions and how they relate to cardinality. So the first thing that I want to do is I want to define something about cardinality. If I let A be a set, the cardinality of A is denoted by putting absolute values around the set A. Now, if A is an infinite set, cardinality is a fairly subtle concept, and we're not going to worry about that in this particular video. But if A happens to be a finite set, then the cardinality of A is very easy to understand. The cardinality of A is nothing more than the number of elements inside the set A. Again, if A is not a finite set, cardinality takes a lot more effort to define, and that's beyond the scope of what I want to cover in this particular video. What I want in this video is I want to look at several theorems about functions on finite sets, and some of them extend to infinite sets and some of them don't, but I'm not going to worry about that. I'm going to mainly worry about the finite set case. So our first theorem is going to be a theorem about one-to-one functions. So we're going to let A and B be finite sets. And we are going to assume that we have a function from A to B that is 1 to 1. Then it turns out that the cardinality of A is less than or equal to the cardinality of B. And we can kind of illustrate why this works rather than doing a formal proof by simply thinking about what one-to-one functions mean. In arrow diagrams, F is 1 to 1 means each B has 0 or 1 incoming arrows. And so if I'm thinking about the elements in B, and I'm thinking about the elements in A, I can do one element in A goes to a separate element in B each time, but I could also have a bunch of additional elements in B. And so when you look at that particular picture, you realize that, yeah, the number of things in A is less than or equal to the number of things in B. Our second picture is going to, our second theorem is going to concern functions that are onto. So if A and B are finite sets, and F goes from A to B is an onto function, then the number of things in A has to be at least as big as the number of things in B. And again, I don't want to do a formal proof, but I do want to kind of do an arrow diagram illustration of why this theorem works the way it does. And again, what I want to think about is what does F is onto mean in terms of arrow diagrams? F is onto means that for each B inside set B, there is at least one incoming arrow. So I'm going to put some things over here in B, and we're going to let this guy have 2 incoming arrows. And we'll let this guy have 1 incoming arrow. And this guy is going to have 1 incoming arrow. And let's make a whole bunch of things. These 3 things down here will all go to that 1 element. This is a picture of a function that is clearly onto, And if you start looking at the number of things in A and the number of things in B, it's pretty easy to realize that the number of things in A is bigger than the number of things in B. Our third theorem concerns functions that are both one-to-one and onto. So again, let's let A and B be finite sets. If f goes from A to B is both one-to-one and onto, in other words, if f is a bijection, then the cardinality of A and the cardinality of B have to be the same thing. Again, in arrow diagrams, if that's A and this is B, if I'm thinking about what the two different things mean, and I'm going to put those in different colors, f is one-to-one is going to tell me that each B has 0 or 1 incoming arrows, and f is onto is going to say each B has at least 1 incoming arrow. If I think about what these two statements mean, so let me get another color here. If I think about what these two statements together mean, this one and this one, I have to have 0 or 1 incoming arrows, and I also can't have, I have to have at least 1 incoming arrow, and I can have no more than 1 incoming arrow. So you put them together and you see that each B has exactly 1 incoming arrow. So what does that actually mean? Well, that means if I look at the elements over here, there's only 1 incoming arrow for each of them. But now I also want to think about what function means. No thing in A can create 2 arrows, so we have to have exactly the same number of things in A as in B for this thing to work. In other words, if you start looking at this picture, you do realize that we have that A and B have exactly the same number of elements. And we're now going to turn our attention to one last theorem, which concerns functions from a finite set back to itself. So we're going to let A be a finite set, and we're going to assume that f goes from A to A is a function. Then it turns out that f is one-to-one if and only if f is onto. So the importance of this theorem is that if you know this is true, then you also know that f is onto. So if you know that f is one-to-one, you can conclude that f is onto. But if you know that f is onto, you can also conclude that f is one-to-one. And that turns out to be a fairly important fact in areas of discrete mathematics where the sets are finite in size. I don't want to do a formal proof of this particular theorem, but I would like to illustrate it and kind of indicate how the proof sort of works. And I want to break it apart in 2 parts. So we want to turn our attention to the forward direction. In other words, we're looking at A is finite, and f goes from A to A is one-to-one. And we're really wanting to kind of try and figure out why must this f be onto. And I don't really want to try and prove this. I want to basically illustrate what's going on. So the situation is that we have 2 copies of the set A, because A is both the domain and codomain of this function. And what that means is we have exactly the same number of elements in both of these sets. And I want to kind of think about what f is a function means. F is a function means each a inside the, let's see, that's not quite readable, so let's do this. Each a in the left-hand circle has one outgoing arrow. And we can do these arrows in different colors. So there's outgoing arrow 1. Here's outgoing arrow number 2. Here's outgoing arrow number 3. And here's outgoing arrow number 4. Now, what f is 1-to-1 means is that each of the a's inside the target set, so in the right-hand circle, gets 0 or 1 incoming arrow. So when we complete these outgoing arrows, when we complete these guys, none of them can go to the same dot over here. So let's actually see how that's going to work in practice. Well, this outgoing arrow has to land somewhere. Let's make him land there. Now, none of the other arrows can land there. So our second one, I'm going to now make my life easier. The second one's just going to land there. The third arrow is going to land there. And what I want to notice is that that fourth arrow is going to have to cover the very last thing. The fact that the two circles have the same number of dots and that none of these arrows can pile up and leave somebody empty is going to force the idea that there's nobody left uncovered. So what this picture then says is all of the A's in the codomain set in that right-hand circle get exactly one incoming arrow. So that says f is indeed onto. And now if we look at the picture going the other way, we see a similar kind of an argument. So I now want to look at the idea that in the backwards direction, we have A is a finite set, and F goes from A to A is onto, and I want to force F to be 1-to-1. So I want to force the statement F is 1-to-1. Again, I want to start by thinking about the situation is that I have two copies of A, so I have exactly the same number of dots in both of my copies of A. Again, f is a function means each of the A's in the left-hand circle has exactly one outgoing arrow. F is onto means that each A in the right-hand circle has at least one incoming arrow. And so I'm going to start with those incoming arrows. And again, I'm going to put them in colors. So there's an incoming arrow to that element. There's an incoming arrow to that element. There's an incoming arrow to that element. And there's an incoming arrow to this element. And we notice that we've got 4 incoming arrows already. And there's only 4 elements in this set. So I'm going to kind of bring these arrows back, and I know because this is a function, each one of them is going to have an outcoming arrow. So I can't have two of these incoming arrows over here starting at the same place over here. So let's kind of again see what this means in practice. Well, this arrow had to come from somebody. And this arrow had to come from somebody. And that red arrow had to come from somebody. And that green arrow had to come from somebody. And now what I want to notice is I'm out of elements inside the domain. There's no element over here that still needs an assignment. And so that's as many outgoing arrows as I'm allowed for this function. And we notice that, yeah, this is indeed a one-to-one function. So if we look at the picture, we see, and again, I'm going to put the conclusion here, we see f is also one-to-one. So the idea here that's important is that in the finite world, and I kind of want to write this as a final conclusion, if A is finite and f goes from A to A, then one-to-one and onto mean the same thing. It is important to realize that if A is infinite and f goes from A to A, it is quite possible for f to be one-to-one but not onto, and f can be onto but not one-to-one. And so it's important to realize that this hypothesis is critically important, but this is a very important theorem about how functions behave.